1, 2, and 4 are things that we did. Question number 3, we have not covered yet. Okay? So if you look at it and you go, I have no idea. Oh, skills exercise 1, we did not cover. We will cover later, but we just have not covered. Okay? Skill exercise 2, okay, dealing with tubes with open ends and fundamental frequencies and sound and stuff like that. Yes, we did cover that. So this is a fair question. Okay? And there's an electric buzzer that's bouncing back and forth, and there's some different observed frequencies and things like that. I would say this is a fair question. Okay. And the portable radio. Part A is something we did not do, okay, relating the electric field intensity to the intensity of a light wave. It turns out that the electric and magnetic field strengths can relate to the intensity in the watts per meter of the wave or square meter, but we have not done that. Part B, okay, does talk about stuff that we did. It's sort of like the fireworks question, where you get some intensity at a certain distance away, and you want to know what power was created the thing of that intensity a certain distance away. Without part A, that'd be kind of hard to do, but you could remember this isn't about doing the problems; it's about looking at them and seeing how things are asked and stuff. Okay, so part B is something that's similar. I think be able to work on. And problem 3 with the bungee cord and the pulses traveling up and down at different speeds. This is kind of like the speed of sound lab that we just did, with things echoing off the other end. But it's not done with a tube and sound. It's done with a cord with tension and that sort of thing. Yeah, and this, I would say, the whole thing is something that you'd be able to deal with. Good. Thank you. Thanks for bringing that up, too. I graded the lab over the weekend. First comment is somebody sent in the lab, okay? And I did a reply all to whoever sent in the lab. What works best is if the person who sends in the lab includes everybody else in the lab group on the email. That way, when I do a reply all, okay, you can see that, everybody can see the response, okay? Right now, I did a reply all to whoever sent in the lab, so if you included your whole lab group, which one group did, you all saw it, okay? And for the rest of you, whoever it was that sent in the lab got the reply, and so you should talk to them about that, okay? The other thing that this saves is somebody sending in the lab and other people not knowing whether or not somebody sent in the lab and sending it in again or that sort of thing. There was one group who had that sort of issue, and I ended up grading your lab twice. But I took the latest one, which had the, there wasn't a whole lot that changed between the first and the last one, but I did look at the latest one. If you send in your lab and everybody's included, then everybody knows, okay, that that it was sent in, and they don't have to worry about whether or not the person who said they were going to send it in actually followed up. Okay, so that would be great if you were to do that. The other thing that would be useful is to send your labs in PDF form. I think it was like 3 groups used PDF and 3 used some sort of Microsoft Word format. And of those, 2 of the Microsoft Word formats, I think I read everything perfectly. The other one, it was pretty clear that the graphs were missing. Okay, so I let the person know, and some photographs were taken and that sort of thing. Okay, but problem is, the world used to be a different place. Okay, prior to like 2007 or so, Microsoft had this strict policy of not changing the Microsoft Word format. Okay, and so if you bought a copy of, or they might add some things to it, but they never took out any of the older stuff. Okay, and so if you created something with an older version, any version could read it, okay? And if you had a new version, the only thing that couldn't be read by the older stuff was the brand new features that were in it, but all the old stuff like graphs and things worked fine, okay? So in that case, when I first started teaching in like 2002, Microsoft Word format was great. Somewhere around 2007, 2008, I started opening up docx files on a copy of Microsoft Word, and if it wasn't created by the same copy, sometimes things were missing. And it tended to be the graphs, okay? It tended to be the images, which were a large part of the lab. So, so if you use PDF format, that will be fantastic. The other thing that happened, luckily at that time, was Microsoft and other people started building in saving as PDF as a standard. So you should be able to do that. Anyway, please do that. That way I don't end up opening up your lab and finding that the parts of it are missing, okay? Then the other thing I would like to talk about is I'm going to briefly go over the 5 sections and talk about things, and particularly in light of some of the things that I saw that bothered me. And while I'm doing it, I will also talk about the next lab that's coming up, and hopefully, after being through one cycle, things will get more clear. Labs that had the best grades were the ones that had sent in a draft copy for me to review, which helped clarify the types of things I was looking for. So I would, whatever you decide to do, I would recommend, we're going to leave this part here and start over here. The introduction. You want to say what you're measuring and comparing. And so you'll make a prediction as to how some things are going to compare. With this lab, the Simple Harmonic Motion Lab, there were 3 parts. One was you measure K using delta X versus M. Okay. 2 is that you compare T versus M to theory, and then 3 you had a prediction of X, V, and A, and then you compare to actual motion. Okay. So I would expect that you would write something. We're going to measure this position and displacement. We're going to use that to figure out the spring constant. Okay. We're going to compare T to M using the theory. There was a formula in the lab manual and in the book, and that we talked about, that said that T is equal to, I believe, 2 pi square root of K over M. Okay. There were a number of people that said, well, we're going to compare T and M, and I expect they're going to be linear. That's a funny thing to expect, okay? Because this formula says that, I've got that backwards. It's M over K, isn't it? that's a funny thing to expect because we got this square root. If it was 2 pi m over k, then you'd expect it to be linear. But many people then did is said t squared is 2 pi squared m over k, okay? And in that case, a good comparison to your theory is that t squared versus m should be linear, and the slope of a graph, if you were to plot t squared versus m, it should have a slope. That should be the slope. So anyway, if you gave me the comparison should be based on the theory. It shouldn't be just something that you go, I wonder if, okay? Some people suggested that things were exponential or stuff like that. If it's exponential, then we're thinking maybe t is equal to e to the a m, where a is some sort of constant. I'd say that's an exponential relationship. But our theory didn't say that, okay? So people going, this is exponential. I was like, what are you basing this on? Okay, so you want to base with the formal labs, we should have developed a theory, and you're trying to test the theory. You're not trying to make up a brand new one, okay? Good. This one, there were some formulas. X is equal to a cosine square root of k over m times t. Okay, or, yeah, so that would work. Or there are other ways of writing it in terms of frequency. You can then say, all right, I'm going to plot this graph, and then I'm going to compare it to what I actually measured. Okay, there's a similar one for V and A. Actually, most people did this one pretty well. Okay, said, all right, I'm going to plot this and then compare to what I got. Okay. So anyway, that was the type of thing I was looking for in the introduction. For the procedure, you were going to write up
Did anyone get a perfect score?
Nobody got a perfect score. There were a number that were pretty close, okay? I think I got some like 9.5s and 9.75s, which were like, you guys are really doing great, but there are some things that would be nice to fix up, okay? All right. Right, so the procedure, tell me what you really did. And how you measured things. And how you estimated uncertainties. And in general, people did pretty good with this. Okay, so for example, suppose you were doing this and you're measuring K by measuring the displacement versus the mass. Okay, you could say that as we were doing that part, we picked a particular spring, we hung the spring from a bar, we then put different masses on the spring. We weighed the masses on the balance and recorded them to plus or minus a tenth of a gram. Or we read the numbers on it, hoped they were right. Since they were listed to a gram, it would have been plus or minus a gram, right? Okay, so however it was that you measured the mass. Then, you measured the displacement. I used a meter stick. I measured to the bottom of the curved part of the spring. The curved part of the spring was kind of hard to see, so I think I could get it to within 2 or 3 millimeters. So my measurements are in millimeters plus or minus 2 or 3 millimeters. Okay? Or you might say we put a piece of tape on the bottom of the spring that gave it a sharp edge. The piece of tape moved in sync with the bottom of the spring, so it stayed, with it. And so I think I've got my measurements plus or minus 1 millimeter. Whatever it was you did, okay? But I want you to talk about how you made your measurement, how you estimated the uncertainty, and this should be in a quantitative way. And specific. Okay? So, there are a lot of things that can go into making something hard to measure. So talk to me about what it was that you encountered specifically. Sometimes people like to say, well, there were errors. I want to know what errors. And error, do you mean mistakes? Or do you mean something that was hard to do? Okay, because they're different. If there were errors, if you say, I measured that and there was an error with measuring it, I'm like, well, why didn't you go measure it again? Right? Okay? But if you say, I measured it and it was really hard to measure and there's some uncertainties associated with it, then I'm good with that. And then I want to know, well, how big do you think the uncertainty is? People sometimes, how do you estimate something? That's, basically, how do you say, I know something about something that your claim, uncertainty is something you don't know. How can you claim to know something about it? But it turns out you really can't, okay? If I'm using this meter stick to measure this edge, okay, I can say, that edge is rounded, okay? But I can measure it to at least a centimeter because it's got a width that's, this edge in particular here is beveled, and it's got a width that's about 2 or 3 millimeters. So plus or minus a centimeter is easily obtainable, right? Plus or minus, and you go, I don't know anything. I bet you can get it to within a kilometer, because it's, really, when you think about it, because you can't measure something exactly doesn't mean you can't measure it at all, right? So I want you to tell me, well, how well do I believe in my measurement, okay? And so how well was I able to actually perform it, okay? So that's what I was looking in there. So you don't, sure, there are some human errors with doing this, but be specific. The human error was, if my eye has difficulty sensing, what's going on with the rounded part of this, okay? Or, well, then there's also, the meter stick is only to, 2 millimeters, so it's hard to measure beyond that. But tell me, don't give me vague errors. The equipment was bad and I'm not perfect is not enough, okay? Tell me why you, how good you were able to make a measurement, okay? And why you think you were that good. Yeah? Okay. Data is just the measurements you took. Okay, so you took, I would have expected a data table here, okay? And a data table here, here was a period, here was a mass we put on it, here was a period we measured, here was the mass that was on it, that sort of thing. In this one, I would expect the graphs, and I think we talked about how when you took your actual measurements, there were, say, thousands of data points, and you didn't need to print those out, but the graph would be sufficient for that, okay? The analysis is how you used the data to make the comparison in the introduction. So many of you say, all right, I'm going to measure K, okay? So this would be the graph, okay? You take the data table that you have up here and you make the graph. When you do that data table, a number of people did something like this. They plotted the number of newtons that was on the spring versus delta x, the displacement, and they did it with these error bars. And you draw a best fit line, and then you also draw these bounding lines, okay? And use the method of this little d over that big D. So you go uncertainty in delta x is equal to little d over d. Okay? So this is in the appendix to the lab manual that I posted on Canvas. Okay? And I helped walk some of you through it. And from what I read, I think there were a few of you that didn't do it at all. There were a few of you that did it but couldn't figure out how to get Excel to draw these lines. I don't know how to get Excel to draw those lines either. And so you didn't include them in your graph, okay? I'd really like to see those, okay? So there are ways of addressing that. You could print out the graph, you could hand it in separately, and with the sketch, with these lines drawn in, okay? You could, some people did graphs completely on graph paper, okay, and you can just sketch the lines in like that. Most people I know end up sketching them in. It takes less than 5 minutes to draw them and make these measurements, okay? If you're gonna make these measurements and have them be reasonable, your graph needs to be big, okay? Some people were doing these little tiny thumbnail graphs or graphs that were like 3x5 card type things. Since you're gonna do this type of thing on the graph, the graph would do better if it were full page. Yeah? Okay? Good. If you don't know, if you haven't done this before, okay, then you can talk to me about it. I'd be happy to walk you through it. Okay? This is a really powerful technique for analyzing your measured data. Okay? Good. This one, you did the same thing. You'd end up plotting t² versus m, measuring the slope. You could then have a measured slope, it'd be so many seconds squared per kilogram, and then you could look at this, okay? And this number, 2 pi squared over k, and it should be about the same, okay? That has an uncertainty, this slope, okay, that you measured, and k has an uncertainty, because you just measured it over here, okay? And so when you say, this slope should be this value, because that's uncertain, your prediction is a little uncertain, okay? And your measurement of the slope is uncertain, and hopefully they overlapped, okay? Good. These, you're just gonna have to sort, I think I asked you to look at the amplitude, the period, and the phase. So this had a certain prediction. When you plot this graph, it oscillates back and forth, and it goes between certain values. Did your actual measured graph go between those values? For velocity, did your predicted graph go between the same values of your velocity? This repeats after a certain amount of time. Did your measured graph repeat after the same amount of time? The velocity and the position were out of phase by 90 degrees. When this was at its maximum, this was at a minimum, or this was at 0. When this was at a minimum, and this was at some positive value maximum, this is at some negative value maximum. Okay. So did your actual measurements have that behavior as well? Okay. So that's the type of thing I was looking for. In your conclusion, tell me your numerical results. So, we measured K, it was this, so many newtons per meter plus or minus so many newtons per meter. We wanted to verify that t² was proportional to m. We measured the slope of our graph of this, and we had a predicted slope of this, and they matched, okay? Tell me that the amplitudes matched and the phases behaved right, that sort of thing. But your conclusion should be numerical. Does that make more sense? Let's talk about the speed of sound lab, okay? For the introduction, what are you gonna, you're measuring the speed of sound in 2 different ways, right? Okay, so I think that's pretty much what the introduction should say. We're gonna measure the speed of sound. One way, we're gonna use a tube and set up some standing waves. The other way, we're going to send pulses back and forth down a tube and listen for their echoes, okay? Your procedure, you're gonna tell me how you did it. okay? You're gonna tell me how you measured something and how you estimated the uncertainty. When you were listening for the resonance due to the standing wave in the tube, you were adjusting the height of the basically the column of air, okay? And you were measuring what that height of the column of air is. It was probably plus or minus a certain amount. What, could you get it down to millimeters? Fractions of a millimeter? How close could you get? One of the problems with that was that the resonance phenomena occurred over the space of maybe a centimeter or so, right? It wasn't a sharp value, right? If you had it at 11 centimeters, 11.5 sounded somewhat resonant as well, okay? So your measurements might be off by a centimeter or more, not because your tube wasn't labeled well enough, but because the thing you were listening for wasn't as sharp to say, it's there at 11 centimeters, but it's not there at 11 centimeters and 1 millimeter, right? It was still there, right? Okay? So you have a range of where you could hear it, and that gives you the uncertainty in that measurement, right? Okay. Good, so you're gonna tell me how you measured things. For the echoes, you use the data that you got from the computer, okay? It was, plus or minus so many milliseconds, right? So that limits, how well you know how long the echo took. Okay? I will also point out that there was a footnote in the lab. If you haven't found and read and used the footnote, you should. Yeah? Okay, if you don't know what I'm talking about, make a note to go and find and read and use the footnote, okay? Good. Data that you took, probably in both cases these will be tables, right? The analysis. For the analysis, you're going to have to take the data in your table and ultimately get it to be a speed of sound. In neither case do you need a graph. Okay? So in this one, we're not going to have we varied this and this varied and the slope of the graph is going to give us the speed of sound. Instead, you've got each individual standing wave that you created gave you an independent measurement of the speed of sound. Okay? And really the best you can do is sort of estimate what they are with the uncertainty and average them. Okay? With the echo, each echo that you find gives you a measurement of the speed of sound, and you can estimate what those are with uncertainty and average them. So you don't need to worry about a graph in the next one. Okay? In the conclusion, part 1 tells me the speed of sound is 340 meters per second, part plus or minus 8 meters per second, something like that. Part 2 said the speed of sound is 336 meters per second, plus or minus 12 meters per second. These overlap each other. It appears that this is about the speed of sound and it's constant. Your book says the speed of sound is 343 meters per second. Is that always true? No? What causes the speed of sound to vary? Temperature?
The material
The material.
or the
Okay.
medium?
The medium, so the medium for the book is air, and actually for us too, okay? If we used, I think we talked about using like helium gas or something, the speed of sound would vary, due to that, okay? But for temperature, I don't know what the temperature was in the room that day. What else causes the speed of sound to vary?
Humidity?
Humidity? Did you measure the humidity? No. Okay, neither did I. Okay, anything else? Pressure changes, the ambient air pressure, the barometric pressure, okay, which is somewhat related to your altitude, okay? Those things I did not measure. I didn't expect you to measure. So if you get a speed of sound that's 338, or, does it mean you messed up because it's not very close to 343? No, not necessarily. In fact, if you got both measurements saying that the speed of sound is 338, or between 338 and 337, then it may be that that's about what it was in the room that night, and that because And this 343 is just at typical air pressures and temperatures.
20 degrees Celsius.
20 degrees Celsius, 1 atmosphere, exactly, okay? But that we were probably pretty close to that, but not exactly there. Good? Questions about that? Send me a draft. I'd be happy to look at a draft. I'd be happy to, I think this one's due, a week from tomorrow, okay? So, over the weekend or something, get it and let me know. Good? Cool. All right. All right, I made notes about the things that we did, so. Hey! There it is. Okay, so we started off talking about the differences between oscillations and simple harmonic motion. We talked about how oscillations repeat, okay, and that you can talk about things like having a period, how many seconds it takes them to repeat, having a frequency, how many cycles per second they go through. And we talked about that there were a lot of things that oscillate, different funny vibrations. We talked about a bouncing ball. If you drop a ball and it bounces up and down, that's an oscillating motion. We talked about some things like throwing a frisbee up so that it comes back down at you. If you kept doing that over and over again, that would be an oscillation. If you get a rubber ball and a paddle and you start with a rubber band and you bounce that back and forth, those are oscillations. Okay? Are they simple harmonic motion? Okay? Well, maybe. Okay? It depends upon, for simple harmonic motion, there was an extra restriction. Okay? So oscillations are a repeating motion. Okay? And simple harmonic motion has a linear restoring force that creates the oscillation. Okay, so we talked about one of them was like a mass on a spring, and if you pull a spring down, it gets pulled back towards the equilibrium spot where it started. But when you pull the spring down, the further you pull it, the harder it gets pulled back, okay, in a linear way. If you pull it twice as hard, or twice as far down, it's pulled back twice as hard. In that case, this will make simple harmonic motion. When you throw the frisbee, okay, the frisbee goes up and it returns, okay, but maybe you throw it up in a particular angle and it comes back down, and it's the force of gravity that's causing it to go, and so this force is constant. It's not like gravity gets twice as weak or twice as strong when it gets twice as far away from your hand. Okay, gravity pretty much is constant over that, and so this is not a linear restoring force. The ball that was going up and down on the ramps, it oscillated, but it didn't have a linear restoring force, and so it didn't make the simple harmonic motion. Okay? So you want to know the difference between that. There were three things that we talked about that did simple harmonic motion. One was a mass on a spring. Okay, one was a pendulum, and one was a physical pendulum. Okay, so the mass on a spring was, you've got some mass and it's sitting at the end of the spring and it's bouncing up and down, like what we did with our lab. The pendulum, you've got a mass on the end of a string and it's swinging back and forth. We saw that for general oscillations, it wasn't simple harmonic motion. But if the oscillations were small, okay, then it was, okay? And by small, 5, 10 degrees, okay? 20, 30, 50 degrees, big oscillations, not simple harmonic motion. But small, it's pretty close. Same with the physical pendulum. The physical pendulum was where instead of having all the mass concentrated at the end, the mass was concentrated at various spots, or the mass is spread out. And so, we did an example with the meter stick, and we let the meter stick swing back and forth, and that was a physical pendulum. Okay? If all the mass were concentrated at that end, it'd be a pendulum, but it's not. It's spread out all over the stick. Okay? And again, the physical pendulum, if you do small oscillations, it's simple harmonic motion. Big ones, it's not. Okay? So, for simple harmonic motion, we saw that the equation of motion for the position, velocity, and accelerations were sinusoidal. Okay, so this it looked something like this. We'd say that the position was equal to a cosine of 2 pi f t, and that v is equal to minus a 2 pi f sine 2 pi f t, and that a is equal to minus a 2 pi f squared cosine 2 pi f t. So these are the equations of motion that describe the velocity, or the position, the velocity, and the acceleration of something doing simple harmonic motion. I believe I did point out that earlier in 114 we had these equations for motion. X is equal to x naught plus v naught t plus 1/2 a t squared. V is equal to v naught plus a t, and a is constant. Okay, so this is SHM. This is constant acceleration. Okay, so you learn to do a lot of things like this in 114. These are the similar type formulas for this simple harmonic motion. Okay, so you'll want to kind of think of those as these are my new when simple harmonic. Actually, I think we also talked about there are a lot of different types of motion. Okay, this one's particularly easy to analyze because we can write down a formula like this. That's nice. It lets us do things. This also, we can write down a formula. It's nice. It lets us do things. These are about the only two types of motion. These are the two most common types of motion that we can actually work with. There are a lot of other kinds of motion that we know are out there, but we don't have the formulas for. Okay? So why do we study these? Because we have the formulas. Okay? So it's nice to take a look at those. Good. So this describes the behavior of the position, velocity, and acceleration. We also found that there were some terms that were useful, and that we could relate to describe the motion. We said that A was the amplitude. Okay, so this is the maximum displacement from equilibrium. We said T is the period, which is the time to repeat. Okay. We said that F is the frequency. Which is the number of repetitions per second. Okay. Good. We talked about omega is equal to 2 pi f. Okay, so this is the frequency in cycles per second. And a cycle is a whole revolution or a whole way around a whole repetition of the whole thing, okay? And this omega is in radians per second. So 2 pi times each thing around gives you how many radians you went through, right? Okay, so that's how that works. It turns out that when you're writing these formula, okay, if you write them in terms of omega, it's much more compact. This is a cosine omega t, a omega sine omega t, and so forth. Okay. Also, it turns out that for these, the mass on a spring, the pendulum, and the physical pendulum, there were easy formulas for omega. Okay. For the mass on a spring, we were able to say that omega is equal to the square root of k over m, okay, where that's spring constant and the mass. For the pendulum, omega is the square root of g, the acceleration of gravity over the length of the string. Okay, and for the physical pendulum, omega is equal to the square root of mg d over I, which is the moment of inertia. Good. So, all right, so those things did simple harmonic motion, okay? They behave according to this. We've got these things to label them. Simple harmonic motion, we assumed went on forever and ever. The amplitude never diminished, okay? And then we talked about, well, in real life, when you get something in this harmonic motion, there tend to be things that cause things like friction or air resistance or something that cause the motion to decrease over time. Okay? The most common thing to happen is for that amplitude to decrease exponentially. Okay? So decreasing exponentially, so what we'd say is damped motion is position is equal to A, the amplitude, e to the minus t over tau, okay, cosine omega t. Okay? So A cosine omega t is pretty much what we had before, okay, A cosine 2 pi f t, or omega t. Okay, but it's got this additional factor of e to the minus t over tau. The way this works is as time goes on, this you can also think of, e to the negative power is like 1 over e to a positive power. So you're dividing by larger and larger powers of e, okay? And essentially the amplitude is decreasing, okay? What a graph of that would look like is something like this. It would start off higher amplitude, and then it would die down to a smaller amplitude. and if you were to graph, sort of how is that amplitude dying off, this is e to the minus t over tau. Okay. We didn't do a whole lot numerically with this, okay? We looked at it and talked about it some, and so I'm not, most of what we did was with the previous stuff, okay? So I'm expecting a casual knowledge of the damping, but not, we didn't do any really diving in deep to that sort of thing. The other phenomenon that we talked about was resonance, and again, you want to know this sort of conceptually. We didn't even talk about that numerically at all, but we did talk about how if you had a damped system, a normal system where the amplitude dies down, and you drive it, you shake it at the frequency that it naturally responds to, okay, then those amplitudes get bigger and bigger and bigger, okay, as you're shaking it along with the way that it's going, okay, and you end up with very big oscillations. If you shake it at a different frequency, then the oscillations don't grow so big, okay? And we talked about how if you were on a swing set and you move your legs in sync with the way the swing is going, that is you create resonance and you swing higher and higher. If you move your legs at a different frequency, it doesn't work, okay? We also talked about how a number of things get into resonance and that can cause a problem, and you want to stop that from happening. We talked about shaking bridges, we talked about cars and shock absorbers and that sort of thing. And essentially what you want to do is if you are hitting resonance at a particular frequency, say driving a car on I-5 in Seattle where the seams occur every 40 feet, okay, then you may need to change the damping, change your shock absorbers, okay, so that hitting those seams at that frequency doesn't cause resonance with your car, okay? If you're building a bridge, you may need to brace it at certain intervals so that it doesn't shake in certain modes of vibration, okay? Or you may need to attach things to stop it from shaking as much. Okay. Good. All right. So that was oscillations and simple harmonic motion. We then talked about traveling waves. Okay. We talked about four situations where we encountered traveling waves. One is on a string. Okay. One was water. Okay. One was sound. And one was light. Okay. So we talked about all of these things had a medium, okay? Okay, medium in the case of the string was the string itself, okay? With the water, it's the surface of the water. With the sound, it's the air, okay? With the light, it's the electromagnetic fields. We did not heavily discuss light. We talked about it a little bit. So while I'm doing this review, I will point out what I consider fair that we did discuss with light, and then the rest, just so that you know what part to look at, okay? But mostly, the book was not very, it was pretty light on light, okay? And so I'm gonna be pretty light on light too. Okay. Some interesting things about these waves are the dimensionality. Okay, this is a one-dimensional thing, the wave going down the string. It doesn't spread out. Water waves are two-dimensional. Okay, sound waves are three-dimensional. Right? So the water waves, you have a source. You throw a rock in the water, you dip your finger in the water, and the waves spread out on the surface. But they don't go up above, they don't go down below. right? They sit on the surface. The sound waves go in all directions around you. They go three-dimensionally around whatever it is that's making the noise, right? Light waves, the same thing, right? As long as there isn't something blocking it. If I've got a bare bulb here, you see the light all the way around in three dimensions. So that's also 3D. All of these things have a velocity. Okay? Two of these, sound, as far as the book goes, it says the velocity is 343 meters per second. Okay? That's on your formula sheet. We talked about how that isn't a hard and fast thing, but it's a reasonably approximate thing for the speed of sound in air at standard temperature and pressure. Okay? Speed of light is also on your formula sheet. It's 3 times 10 to the 8th meters per second. Turns out that that one is actually a hard and fast rule, and everybody sees it go in the same way, which is really weird. Okay, we won't get into the weirdness of it, but if you do, you're starting down the path of relativity. Okay, and if you every once in a while. Especially in this class, as we get into modern physics, people go, oh, I want to do some relativity. If you do, it's outside the scope of the chapters that we do, but I'm happy to help you along. And the book will support you. Okay? So if you want to, just let me know. Okay? The velocity of water waves, we did not talk about those. Okay? So don't worry about this. If I were to say water waves do have a velocity, if I were to ask you about something on an exam, I would either give you a water velocity or you would find it through some other means. There is not a formula for the velocity of water waves that you're expected to have. Good? Okay. There is one though for waves on a string. We have V is equal to the square root of the tension over the mass density. Okay? So this mass density is the total mass of the string over the length. This one I do expect you to know how to use. It is on the formula sheet. Okay, so be aware of that. Okay. All right, so these waves travel in the medium at a particular velocity. The waves can be pulses, okay, in which case the pulse would have a particular shape and you just watch it go down the medium. Or sometimes the wave is due to somebody shaking something up and down at a regular rate. Okay? If that's happening, if the source is shaking up and down at a regular rate, then the waves look sinusoidal. Okay? And so for the sinusoidal waves, there were some properties that we could talk about. We could say that the wave would look like this spatially, so this is the position, okay? We could say that this distance here is the amplitude, okay? How much this is, maybe the position it's going in, and this is y, the amount of displacement. So this might be how much the spring is disturbed. This might be a high pressure and low pressure of a sound wave, okay? But the thing that's on the vertical axis is whatever's being displaced from the equilibrium, and then this is a spatial axis. We talked about how this distance here, we could call lambda the wavelength, okay? It's the distance with which something repeats, okay? This is kind of related to the period. The period is the time it takes something to repeat, okay? Good. So, like with simple harmonic motion, we did have a formula for what the wave looked like, okay? For y, the displacement of the wave. But this is changing not only as you look at different positions, but also as time is going on. So this function of y was of x and t, okay? And it looked something like this. It said the position is, the y, the displacement, is equal to the amplitude times the cosine and of 2 pi And then what we have is T over, wait, 2 pi. X over the wavelength, okay, minus T over the period. Okay? So every time T over the, every time you go you wait T seconds, okay, this piece goes by 1, 2, or if you wait T seconds, or 2 T seconds, or 3 T seconds, this causes that argument to the cosine to alternate by 2 pi. Okay? When I move down 1 wavelength, 2 wavelengths, 3 wavelengths, each time I move down a wavelength, this goes by 2 pi. Okay? So this causes repetition per wavelength and per time. Okay? And it ends up being the formula for a wave that's traveling down a string, or a water wave that's traveling on the water, or even a sound wave or a light wave. Okay, this is general to all sinusoidal wave motions. And I made up the exam over the weekend. This formula is not on your formula sheet, but I put it on the exam. Okay, and you might even think, gee, why would he have put that on the exam? And it's for the reason that you think. Okay, you got it?
For our own good?
No, I'm being straightforward here, and I want you to know that you will find this, so don't worry about memorizing it. But this is also a hint, okay, that you probably want to look at what you can do with that formula, okay? Because you can use it to, if you know something about the shape of the wave, if you know what its wavelength is and you know what its period is, you can come up with this equation, right? Okay, so you'd want to be familiar with looking at this equation and relating it to graphs. Boy, I've said a lot, okay? It's a short class, so I'm trying to give you some help. Any other help? Yes, so stay tuned, okay? I will. You can make all kinds of bad wave puns, can't you? Yeah. Okay, all right. I've learned to just live with it. So any sinusoidal wave you can describe this way. The other thing that comes from sort of the geometry of the situation is that another expression of the velocity would be that the frequency times the wavelength ought to give you the velocity. If it repeats in space through this many meters, and this is how many repetitions you get per second, okay, then this times that should give you the number of meters per second that the pulses travel. The rate at which the pulses travel, okay? So this also works for light waves, sound waves, string waves, water waves, whatever, okay? And this one is on the formula sheet, so I left it there, okay? Good, okay? So, all right, so that talked about the shapes and the way they travel, and that sort of thing. We also talked about how these waves that spread out reduce in intensity as they get further away from the source. Okay? So we talked about how you can say that the intensity of a wave is equal to the power at the source. So this is power at source. In watts. Okay, this is the intensity is in watts per square meter, so watts per meter squared. And if you take the power and you divide by the surface area of a sphere at a certain distance away, okay, that would tell you how the watts is being spread out over that many square meters. Okay. The surface area of a sphere is 4 pi r squared, okay? So we end up with the intensity is the power over 4 pi r squared. This is the surface area. And so when we were dealing with the firework problem and we talked about that, there was a certain intensity that we heard and we were this far away, what was the power? Okay? On the problem that dealt with radio waves, we didn't talk about some of the details of radio waves, but one of the things dealt with intensity. It said the intensity that the radio receiver can measure is so many watts per meter, and the power of the radio station is so many kilowatts. So how far away can you tune your radio? Okay? So I mean, these are the same types of things. For sound, there is a logarithmic scale that you use to measure the intensity. It says that beta is equal to 10 times the log of I over I naught. Okay? So this beta is a sound level in decibels. Okay? This is log base 10. You have instructed me not to put a number 10 by there because you like log to indicate that it's 10, but don't confuse this with natural log, LN. Okay? This is log base 10. Okay? Right? And on your calculator it would be labeled log. I naught is a reference intensity. It's on your formula sheet. It is 1 times 10 to the minus 12 watts per square meter. Okay? And people will call that the threshold of hearing. So basically, anything that is a smaller intensity of this, you have virtually no hope in hearing. Maybe some people with super hearing abilities can do it, but it's right on that edge. Okay, this sort of limit of hearing and it varies person to person. Some people are a little better or a little greater, but nobody's that great. Okay, so this is about where it cuts off. Anyway, these intensities can, as these go up by huge amounts, the decibel level doesn't go up by huge amounts. Okay, the typical decibel levels are between 50 and 100. Okay, as opposed to between something like 1 times 10 to the minus 6 to 1 times 10 to the minus 2, watts per square meter. Okay, so anyway, it's a different way of looking at that. Good. We also talked about how the appearance of the frequency, or the frequency that you hear, depends upon the motion of the source. It turns out that this Doppler effect, we talked about the Doppler effect. Okay. The Doppler effect, we talked about it only in the context of sound waves. Okay. As it is written, it works the same way with water waves and waves on a string. Okay. There is a Doppler effect for light waves, but it's not the same formula. Okay. So if I'm asking, if tomorrow you get something, I need the Doppler effect for light, you're doing it wrong. Okay, because we haven't talked about the Doppler effect for light. Okay. It turns out, remember me saying that these speeds vary according to different effects of the media and stuff, but light is special and weird. The special weird part of light makes its Doppler effect special and weird. Okay? Good. I'm not asking the Doppler effect question with light, so don't worry about it. Okay, but Doppler effect with sound is fair game, and there were two formulas, and really there was a bit of understanding why this occurs and a bit of how to read a more complicated formula. So the two that are on your formula sheet are F is equal to Fs over 1 minus plus Vs over V. Okay? And the other one is that F is equal to 1 plus or minus V observed over V times Fs, okay? So this is the frequency of the source. Okay, and this is the frequency observer hears. Okay. So in both cases, what you end up with is the frequency of the observer hears. What goes in is the frequency of the source. This V is the velocity of sound. Okay, this is how fast sound propagates. So V is the velocity of sound. That V as well, okay? This V observed this is the frequency that the observer hears due to the observer's motion, right? So the source is sitting still and the observer's moving, okay? So this is the velocity of the observer. Okay. And this Vs is the velocity of the source. Okay. In all cases, you would say, these are really speeds, okay? You're not velocities. I know they're labeled V, but they are unsigned, okay? So you'd say, you know, this observer is moving at 5 meters per second, and then you'd say it's either away or towards, okay? What you would do is use the top sign for towards, and the bottom sign for away. Okay? So if you were to say, the observer is moving at 5 meters per second towards the source, okay, then you would use this plus. Okay? If they're moving at 5 meters per second away, then you use the minus sign. If in here, if they're moving towards, use the top sign, which is minus. If they're away, use the bottom sign. Yeah? Okay? Those are some rules, okay, for applying the formula. If you're confused or you want to just sort of double check that it's making sense, remember that if the objects are moving towards each other, the pitch is going to be higher. The wavefronts are coming faster than what you would expect. If they're going further apart, they should be getting smaller, or they should be getting less. Yes? Okay. Good?
Question. Velocity of the source up there?
Velocity of the source, velocity of the observer. And then this is just the velocity of sound, the V.
So there's two oh no.
There's two velocities, right. The sound goes at a certain speed, and then the observer is moving towards and away. If the observer or the source is moving faster than the speed of sound, then this doesn't work. Okay? And you have sonic booms and other things. That's discussed a little bit in the book, but I didn't discuss it.
Are we using the same equation sheet as this?
You are using that equation sheet.
Because it's kind of complicated on this one, how they have it written out. I'm wondering if you can redo that and maybe put it on the fastest one. I think this is the same one, but it's.
Put them together.
Oh my
yeah,
gosh.
It's really confusing there. So.
I'll write that on the board, okay?
Yeah.
I'll write that on the board tomorrow. If I forget, tell me about it,
Okay.
okay?
Can we use the one that we've been doing notes on?
Nope.
No.
So I will give you a formula sheet. If we come up with some things like this, I'm happy to correct them by writing them on the board, okay, or make some things. But I want everybody to, I don't want everybody making their own formula sheets, okay? And I can actually talk to that for a couple of different reasons. First of all, I'd like people to be able to, everybody to have the same sort of stuff to reason from, okay? Second of all, I've found that in a lot of cases, students do not do a good job of making formula sheets. They put more than they should on it, and they put formulas that are very specific to certain things in a textbook, this worked for that problem because of some assumptions that were made for that problem, and it doesn't apply, okay? And so they end up very frustrated. They come up with this, 100 different equations, most of which only apply to very specific equations or situations.
Mhm.
Sorry, that's just how I do it.
Yep.
Okay. Good? Question? Yeah.
You put on their top sign boards, that first one,
Yes?
is it still supposed to be negative?
Yep, that one's negative, that one's positive. Yeah? One of my very complicated thing, I combined them two together, didn't I?
Yeah, it's pretty wild.
Yeah, and one of them's got the, I got them, yeah, the plus and minuses are swapped like that.
Yeah, yeah,
Yeah, but it,
Yeah,
if you
that's
look
right,
at it
that's
for
just-
just a little
that's
bit,
just
you'll go,
confusing.
oh yeah, that's the same thing.
yeah.
Yeah, yeah. Okay. Good, okay, so where are we? Right. Next, we talked about superposition. Okay, we talked about how as two pulses are going towards each other, they pass through each other, okay? And you add the amplitudes as they were going through each other, they could cancel out, they could get to be a bit bigger, depending on what part was passing through at what time, okay? But that superposition of the waves was what was happening. Okay. We then talked about reflections at ends, okay? And we talked about how sometimes we had an end, like a fixed end of a string, or an open end of a string, or a closed end of a tube, or an open end of a tube, and they reflected the pulses. If you sent some pulse down, it would bounce and come back. We saw it with the spring, we saw it definitely bounced off the other end, okay? And with the tubes, we talked about how that would work. It turns out that the book and other books were a little confused as to what happened with the opened end and the closed end of the tube. And it doesn't really matter to me which one you go with. I'll stick with what I said I was up on, what I was using. I realize the book is doing a reverse, but in no case does it come out with a different answer as far as what's happening with the tube, for a reason we'll discuss in a minute. Okay? But if we have reflections at the ends and we have two ends, if there are two ends, you can create standing waves. Okay, and so we spent some time talking about what was going on with the ends and what type of standing waves we could get, okay? And so we talked about some situations like this, where we had closed ends, okay? And that we could say, if we have some length L, okay, then if these are closed fixed ends, okay, so that these ends had to be nodes, we could say, all right, this is a node, that is a node. The minimum wave that we could put on here would have a single antinode in the middle, and that would reflect back and forth, okay? And so we could say, there's half a wavelength here. One wavelength is a full repetition of a cycle, and so we've only got half of one here. The next most complicated, because if our string has two fixed ends, these ends would have to be nodes. The next most complicated pattern is to have an antinode, node, and an antinode. In between, in between two nodes, there has to be an antinode. So that's the next most complicated pattern. okay? If we draw it, it looks like this, okay? And we go on, now there's one wavelength per L, per length of the string, okay? The next one fits in another antinode and node pair. So you end up with node, node, antinode, node, antinode, node, and antinode, right? So this goes like that, okay? And now you've got, well, 1.5 wavelengths, okay, per length, okay? We talked about how you could count these up and make a formula. Even if you can't make a formula, you can at least count them up and relate length to wavelength. This process of labeling the ends of being a node and an antinode and then counting the wavelengths, I said was very important. And in fact, I think promised you that I would put a problem on the exam where I'd give you a new situation where you could figure out where some nodes and antinodes had to be, and then do this type of thing, okay, to figure out about the wavelength, yeah? Okay? So I would expect that. I told you I was gonna continue to give hints. Okay? So all right, so you want to, if you're going to look at general things, you might want to make sure that you're good with the 3 cases we discussed, okay? The other case we discussed was something where the ends were open, okay? And they looked like this. You could say, well, this has an antinode, node, and an antinode, and then, and essentially it was just the reverse of this. If what we have is an antinode at the end, then we have antinode, antinode, node, antinode, node, and so things would look like this, and again, we'd have one wavelength here, because it's gone back to its repetition in the length. And actually, these look like that. And then the last one we talked about was where these two were different, okay? And so one end was a node and one end was an antinode, okay? Okay. So if you've got, you know, one end like that, and we say, all right, this end's an antinode, and this one has to be a node, then, well, the fundamental would look like that. You just have an antinode and a node. There's no need for any other complicated stuff in between. And you could say, if this is length L, this is 1/4 of a wavelength. So lambda divided by 4, 1/4 of a wavelength, is equal to L, okay? And then you could look at, well, what's the next in the pattern? And if it's this same situation, okay, then this still has to be an antinode, that one's a node, but we can't stick just one thing in between. I've got to go from antinode to node and then back to antinode. So this would be that, okay? So we've got a node here, and an antinode. This is 3/4 of a wavelength is equal to L, right? Because this is half a wavelength and there's a 1/4. So half plus a 1/4 is 3/4. Good. So expect something similar to that, but a different geometry. In case you were worried about, you might go, you know, maybe this should be an antinode and this should be a node, because our book drew it a different way. Well, if you do that, it's still, all it does is switches all the A's to N's and N's to A's, and the pattern is still the same. This is still 1/4 of a wavelength. This is still 3/4 of a wavelength. So I will not take off any points if you do it this way or labeling them the other way, okay? Yeah? So don't worry about that. Yes?
I've seen done some reading and stuff, and there's some discrepancy between like what her first harmonic is. So like, are you considering that top one to be your first harmonic, or that second one where there's a full wavelength?
Yeah, I've seen the same sort of discrepancy in the literature too, as to what exactly constitutes. And you know, your book sort of says, well, this is the fundamental, and this is the second harmonic, and there's one in between that got skipped or something. And I'm not worried, okay? So here's what I'm going to be looking at is, were you able to find the simplest thing you could do? Okay, in that case, this is gonna be this, that's gonna be this, right? And then did you add complication? Did you add, what had to follow from this, okay? If you went from here to there, I'd say you missed one, okay? But if you called this the first harmonic or the second harmonic, I don't care. If you said it goes this, this, and this, and you say these are harmonics, I'm good, okay? I'm not worried about the label, okay? Same with this, right? I'm worried, did you find the right behavior, okay? And in particular, a drawing is probably better than a label. Especially when, as I'm glad you noticed, as you read through the literature, there isn't exact consensus on that. It's frustrating. So, but there is consensus on how it behaves.
Okay.
So get that and you're good, okay? Good. So, along with this, okay, there is still the idea that the velocity would equal f lambda. Okay, so when we were dealing with the speed of sound lab, this became important. We'd say the speed of sound, or the waves on a string, we said, we have some standing waves, there was a frequency, there was a wavelength, there's a velocity. Okay, this again comes from geometry. In any wave on a string, a sound wave, they're all going to have this behavior because it's cycles per second, meters, right? It's going to give you meters per second. Yeah. Good. So we did this with sound waves. We did some of this type of stuff with the waves on a string. And then tonight, we talked about beats, okay, which is a type of interference with two frequencies that are almost, but not exactly the same. Okay, so know what that phenomena is, know that what you would hear, or if this was, some other type of thing, what you would observe is that the intensity would vary between something pretty strong to pretty weak, to pretty strong, but pretty weak. That's actually the difference of those two frequencies. So if they're almost exactly the same, then the beat frequency could be, in the case of the things I was hitting, the frequencies were 440 cycles per second, but the beat frequency was 1 cycle per second because they differed by 1 cycle per second. So every second they alternated between being in and out of phase. Okay? Good. That's the last of the material for the exam. Good?
And so for that one, we just be calculating frequencies, for instance, then you'd ask us like how many cycles it off per
Yeah,
second or something like
this
that.
should be, I just want you to basically know what that is. This seemed like a reasonable thing to do. The next thing we're gonna do with the spatial way that the interference is working is more complicated and falls into things that are done in the next chapter a lot. Good? So maybe a couple of other things about the exam. I give lots of partial credit, okay, so tell me what you're thinking. I grade pictures, okay, so if I can see that you read through whatever I was describing and that I'm not grading pictures for artwork, I'm grading pictures for clarity of explaining what it is that you're doing, right? So as long as your picture lets me know that you understood what I was asking and what you were trying to do, that's a part of solving the problem. If you can't get the picture right, you have a hard time getting started. So that's a skill in and of itself. show all your work, okay? If I can see how you got something, I can tell whether or not you, were doing something fine, and then you lost track of a sign or a factor of 2, but your reasoning was fine, okay? If I see you write down something that was correct, and then pretty quickly go to something that's not correct, and I can tell that there were a lot of steps that you must have done in your head, and I don't know what's going on, I can't give you as much credit. If I can see, when I'm giving partial credit, I sort of classify the errors into two sort of things. One of them is sort of silly mistakes. You lost track of your bookkeeping. The other are conceptual errors. I count off a lot more for conceptual errors than because conceptual errors are, you weren't really sure what you were doing, okay? Bookkeeping errors are, I was doing everything fine and I lost track of a sign, okay? Often I can tell, okay, if you show your work. And if I see a bookkeeping error, okay, then I don't take off very much. If I see an error that's a conceptual error, I'll take off a fair amount. If I see an error and I can't tell, I'm gonna assume it's a conceptual error, okay? And you don't want that. I mean, especially if it wasn't, maybe it was. Sometimes people don't write things down because they don't know what they're doing, in which case, well, you lose the points, okay? But if you're not writing things down because you're trying to do it all in your head, then you're doing yourself a disservice, okay? Because I can give you points for the steps in between if they're done correctly, okay? If you're not used to doing that, get used to doing it. Everybody who wants you to do detailed scientific work wants you to explain how you got it, not just what you got, okay? So this is a habit you want to get into if you're not already into it, okay? During the exam, I don't want anybody bothered by a word that they don't understand, unless it is a, okay.
What
So-
is frequency?
Exactly, okay? So I'm gonna try and describe problems that you could imagine in the real world, okay? To do so, I might invoke some devices that we haven't really talked about. I'm gonna tell you my favorite one because it really made me aware of this type of issue. When I was doing 114 type things, the book often suggests, and I often put in, talk about circular motion problems on a playground merry-go-round, okay? And the first time I put one of those on my exam, I became acutely aware of which countries do not have playground merry-go-rounds when kids are growing up. Because I had to go through and explain what it was, okay? I now am very cautious about playground merry-go-rounds, okay? But I've had other sort of archery questions and stuff like that with projectile motion. And some people get it and some people don't. If I use a word or a technique and you're wondering, what is this, okay? And feel free to ask, okay? Especially for things like the playground merry-go-round or some sort of, I'm happy to explain what the situation is. And if I get a lot of questions, I might draw something on the board and talk to other people. Or so that everybody else can know. What is frequency? That is something that I would say, well, that is one of the terms that we were doing in the lab or in class, and it's something that you should know. Don't be embarrassed. There might be some that are in between, right? And you can, I'm not going to be embarrassed if I say no to you. You don't be embarrassed if I say no to you. I might say yes, in which case it's good to know. Yeah? Okay. If English is not your first language, I do not mind if you use a translator. The translator needs to be a dedicated electronic translator. It cannot be your phone, it cannot be your laptop. Oh, by the way, you also will want a computer. The computer cannot be your phone or it cannot be your laptop. It does not need to be an expensive calculator. The calculator, you want sine, cosine, you want logarithms and exponentials and that sort of thing, but it doesn't need to be a graphing calculator. If you have a graphing calculator, it's fine, but it doesn't need to be. Yes.
Are you gonna post the solutions for the practice exam?
I wasn't planning on, it was many years ago that I gave that with a different
Oh.
book. I don't have this, I don't keep those solutions, and I don't want you focusing on them. If there's a question about just sort of how you'd set something up, I'd be happy to talk about it.
Could you do just the answers? So
Well, I don't
we
know.
know if we.
I'd have to
Oh.
work them through.
Okay,
I do know how to do them,
okay.
okay? And
you
I'd be
do.
happy to share that with you, and that's probably as far as you need to go too.
Right.
Because I'm not gonna answer, you know, what's the point of knowing the answer? You just need to know how to do it.
Yeah.
Yeah. What else? Oh, another thing that people often ask is, are the exams cumulative? And the answer is that the exams are cumulative all the way through, right? So the next, I mean, they kind of have to be. I'm gonna focus on these sort of issues, but there still are things like motion and that sort of thing going on. So remember your Physics 114 and your Physics 115. I'm not going to get all obscure on you, okay, and start asking about, you know, magnetic induction or stuff like that, although I could, it would be fun. But I'm not, okay? And in Physics 123, they take induction and harmonic oscillators and mix them all together, okay? It's kind of cool, okay? But we're not gonna do that. But do be aware of basic constant acceleration motion, basic circular motion, basic concepts with energy. I assume you know what a watt is. I assume you know sort of the basic things from Physics 114 and 115. Not so much 115, more 114, because this is very mechanical, the types of things that we're doing. I expect that if you would know that in addition to finding the velocity of something from one of these waves, you could figure out a velocity based on how many meters it went in how many seconds, right? Okay, if you knew it was constant velocity. If you knew its acceleration was, if its velocity was changing, you know that that's an acceleration, right? Okay, and those sorts of formulas are on the formula sheet. So you might want to just sort of look over the older stuff, especially the basic stuff, and make sure you know where it is and what it is. Yes?
You ask any questions like straight from lab? I mean, obviously the
Oh.
principles are the same, but like things that we've done.
Yeah, so, question was, am I gonna ask something straight from lab? Not straight from lab, but I'm not gonna ask anything straight from homework or straight from an in-class problem. But related to, yes. So often you'll go, oh yeah, we did this on an in-class problem, or we did this in lab, or we did this on some homework, okay? So, yeah, lab is important too, okay? Lab techniques are great. They often, in fact, are a rich source of skill type questions, right? You know, how do you do this? How do you do that? So yeah, lab stuff can be there too. Good? Okay. Like I said, I give lots of partial credit. So, and I'm not,
On multiple choice?
I don't give, not on the multiple choice, but on the other stuff I do. If on a multiple choice question, you're wondering, you want to talk to me about something, I might consider, depending on what you wrote, okay? I believe that all my multiple choice has one answer, okay? But if you're sitting there thinking, I'm on the fence between these two answers because of this or that, and you've got some reasonable stuff to say, I would give partial credit. So yes, you can, you know, it's not a Scantron thing, right? You can write what you want, okay? I know this is gonna sound kind of weird, but the whole class is curved. Exam scores, I've gotta ask these questions that are kind of puzzle type questions. Exam scores tend to be in the 60s to 70s, okay? And that does not mean that everybody's flunking. In fact, it's fine, okay? Exam scores that are in the 60s to 70s typically lead to grades in the class that are in the A's, B's, and C's, okay? So if you're feeling overwhelmed, just do the best you can, answer what you can. If you get 2 out of 3, that's not bad, okay? Because sometimes people get hung up and a lot of times you're in classes where Well, this is the third quarter of physics. You've had a lot of physics exams, right? Some of them have been pretty hard, right? So, you know, you sort of deal with what you get. I'm looking at how you're thinking, not whether you can answer 100%. Sorry, I went to the 114 topic. You guys should know this. We good? Let's take a 5-minute break and then we'll come back and then we'll do an in-class problem.